So today we're going to talk about ancient astronomy. So human beings have been studying the night sky for thousands of years. And as long as 3,000 years ago, the Babylonians, the Assyrians, and the Egyptians were able to calculate the length of a year by carefully watching the motions of the sun and the stars. The Egyptians were even able to correlate the motion of the star Sirius to the flooding of the Nile and use that to help predict when the flooding would occur and when they could plant their crops. The Chinese had a working calendar that correlated with the stars, and it determined the length of the year. This was around the same time as the Egyptians did the same. They also took detailed recordings and data of the comets and meteors, the sunspots, and stars that were faint but then quickly became bright for a short period of time. These are what we now know as supernovas. And their observations continue to be useful to astronomers today, so that we have a longer time frame of knowledge about what has happened in the sky rather than just the more recent couple hundred years. The Mayans created a calendar that was based on the planet Venus, with sites dedicated to observing the planet. This right here is a structure at the site called Chichen Itza. Polynesian astronomers used the night sky to navigate the stars for hundreds of kilometers away from their islands. This is what they use for a compass, and you can see the directions here correlate to certain stars that you might see in the sky. And if you were aiming toward a certain star, that would be the direction that you were moving in. They only had their own senses to make these observations. The telescope was not invented until the time of Copernicus, which was in the 1400s. And because navigation and marking the passage of time and planning things like harvests and planting crops was so important to people of these times, the study of the cosmos, the sky, was very much intertwined with the cultures and religions of these ancient peoples. Some early Greek cosmology. So, cosmology is the study of the cosmos, the structure and the origins of the universe. Greek philosophers gathered evidence that the Earth is round as much as 2,000 years ago. Uh, Aristarchus of Samos, who was around about 300 to 230 BCE, even believed that the Earth moved around the sun, but his idea was rejected by Aristotle and most of the other prominent Greek philosophers. So, why did they reject this idea? Well, one reason is parallax, which we talked about a little bit in the last unit. Basically, it's the apparent shifting of positions because of the observer's change in location. So if you think about Earth, if it were orbiting around the sun, then we might expect to see that prominent stars in our sky, would change location in our sky as a result of that relative to other stars that may be further away. What the ancient people didn't realize is exactly how far away these objects really are from the Earth, and that stellar parallax, is really difficult to observe without extremely sensitive instrumentation and very careful observations, which they just did not have at that time. So they didn't observe stellar parallax, and therefore they believed that the Earth did not revolve around the sun. So, is the Earth flat or is it round? Well, we have some evidence that we can use to figure this out. Even 2,000 years before Christopher Columbus, people did know that the Earth was round. even Aristotle noticed some of this evidence, and that evidence includes the fact that Earth's shadow on the moon appears to be round during a lunar eclipse. So we talked about the idea that the phases of the moon are not caused by Earth's shadow, but a lunar eclipse is caused by Earth's shadow, and the edge of the shadow is, you can barely see a roundness to it. The other piece of evidence that was available to ancient peoples for Earth's roundness is that if you were to be on the open ocean, you wait a minute. Travelers that go a significant distance south, or north, so significantly north or significantly south, are going to see different stars in the sky. And that's because they're just looking at a different area of the sky. And if the Earth were flat, it wouldn't matter if you're going north or south. You would always be looking at the same sky. But if the Earth is round, then you're looking at different places in the sky. And a third one is, which I was about to say, is that travelers on the ocean, if you're looking far away across the ocean and something is approaching you, it looks as if it slowly rises in the horizon and then moves toward you. I don't know if you've ever had that experience where you're on an ocean or maybe even one of the Great Lakes, because they're big enough for this. An object that is floating on that water can be far enough away that it is completely unseen, and then as it gets closer, it rises up a little bit into your view and then moves forward. And that's because of the curvature of the Earth. And the ancients were able to make these observations and could use these observations to conclude that the Earth is round. Another piece of information that they were able to deduce is that the sun is very far away. And how did they know? Well, essentially, they could tell that the sun's light strikes Earth in essentially parallel lines, parallel rays. And the only reason that could happen is if the sun is very, very far away. So imagine if the sun were at this point A, then you would have very different angles of sunlight hitting the Earth, depending on where you are on the Earth. Very different angles. If it were a little bit further away at B, you'd have slightly less variation in the angle of Earth's rays striking the Earth, the sun's rays striking the Earth. For even further, less of a change in the angle. But if the sun is extremely far away, then you start to get essentially parallel lines of light coming at Earth. And the Greeks were able to observe this. The closer the sun would be, the bigger the variation of the sun's rays striking the Earth along Earth's curve. Now, if we were able to get everybody on Earth, on one side of the Earth, to point at the sun at the same time, we would essentially all be pointing in parallel lines. So if we were pointing at the sun from our location in the middle of the day, or any time of day, really, we would all be pointing in the same direction. As long as it were daytime, people near sunset would be pointing this way. People near noon would be also pointing this way. And on the other side of the Earth that we can't see in this picture, people at sunrise would be pointing in the same direction. We're all, and that's because the sun's light comes at us in essentially almost parallel lines. I'm going to move myself again. How big is the Earth? This was another thing that the Greeks were able to estimate by taking some detailed measurements. Eratosthenes was able to estimate Earth's size around 200 BCE, and here is how he did it. He happened to know that the sunlight hit the bottom of a deep well in Syene, Egypt at noon on a specific day of the year. So here is the well right here. It's very deep. And he knew that the sun was striking Earth at a 90-degree angle at that particular time. in order to do this. So then the sun's rays would be coming in toward the exact center of the Earth. At the exact same time, on the exact same day, he was able to measure a shadow of this column in Alexandria, which was about 440 stadia. That was a unit of distance measurement for the ancient Romans. And knowing this distance right here, which we're not exactly well, we can assume we can estimate what it would be in miles or kilometers or meters. But he used this distance, which was known to him, and this angle of shadow from this column in order to figure out what the radius of the Earth was and what this angle might be. And from these measurements, he was able to estimate the radius of the Earth and essentially the diameter of the Earth using geometry, which was a relatively new mathematical language or set of processes at the time. Then there was Hipparchus. I'm going to move myself again. Hipparchus. And he was a great ancient astronomer around 150 BCE. He built an observatory on the island of Rhodes, which is a Greek island, or an island near Greece. He was accurately measured and recorded locations of hundreds of objects in the sky. He gave celestial coordinates for each of the stars, those celestial coordinates that we talked about last unit, similar to the latitude and longitude on Earth. He cataloged the stars according to their apparent magnitude, of how bright they are. This right here looks like a telescope, but it is not actually a telescope because it doesn't have any lenses in it. It was just like a really long tube that would block out extra light from around. So he was able to look at particular points in the sky without the interference of light from other objects in the sky. He noticed that the stars that were directly north of the celestial pole had changed over a course of 150 years. And from that observation, he realized that the Earth undergoes something called precession. And we talked a little bit about that last unit. I'll get into a little bit more about what that means this unit. But Earth basically revolves, and the poles move just a little bit as it revolves. So precession, another couple of pictures that show precession are here. Okay. So Earth's axis wobbles kind of like a top. So if you imagine Earth rotating as a top, here's the South Pole, here's the North Pole. As it rotates around like a top, the direction that this North Pole is pointing traces out a circle in space like that. And that's what we call precession. Right now, our North Pole almost, but not exactly, points at the star Polaris. In about 1400, maybe 1200 years from now, Vega will become our North Star. I won't be around then, but probably. But eventually we'll see Vega as our North Star and maybe some others in between. And about 5,000 years ago, the star Thuban was our North Star. And then the reason that this changes is because of precession. And if you think of like a top, you've seen tops spinning, and they kind of like, as they're spinning, they map out the circle in space. That's the same exact kind of phenomenon.